Hey, Vlad here, devinside.com. Welcome to another video. In the previous video, we have implemented lists and learned a lot about fold right. And today we're going to start with something very similar, but end up somewhere completely different. And also we will write a tiny math library in the process, but don't worry, we're talking high school math here. There will be a lot of new and scary words though, but really it's kind of simple stuff. And the coolest thing about this library is that it's going to test itself. Let's get right to it. As always, we're in the Ubuntu virtual machine and we're running Sublime Text with a plugin called Terminus, which emulates the entire terminal for us, which we use to run SBT, which we use to rerun the test every time we save the file. Now, since the beginning of this YouTube channel, I actually wanted to use my VM in full screen mode like this, but I always had some issues having Sublime fully maximized like that. Recently, I updated my VM and now it actually works. So this way we have way more space, which is really cool. Before we start with this video, I noticed that we've forgotten one thing in the previous video. We changed exist to use fold right, but we forgot about for all. So I'm going to do the same thing for all. So I'm going to just use fold right over here, and I'm also going to swap the predicate and the end like this underscore like that. There we go. All the tests should still be green, so it's exactly the same code basically, but it's a bit more efficient. We're going to start this video by implementing a function that I'm going to call aggregated, and we're going to define it on foldable. And if I scroll up, it's going to be very, very similar to fold, and in fact it's going to be backed by folds. And so in the beginning of the video, in the first part of the video, we're just going to play around with it, and in the second part we're going to implement a tiny math library and we're going to embed it right into our homegrown collections library. Since we've implemented lists in the previous video, we're going to start by going to the list suite like this, which resides in our test folder. Let me reveal it in the sidebar like this. All right, let me go down and I'm just going to go and create a new test like this over here, and let me also collapse the sidebar, create a bit more space like this by scrolling down, and I'm going to call it fold should be able to express aggregation like this. And in fact, maybe we should just switch to running only the list suite like this. Come on, really, one change? You're going to compile it for like 2 minutes? All right, there we go. Let's just go to test only user.list suite like this. All right, cool. Now what we will do in this test is we will play around with a few aggregations with the goal to find a pattern that we can abstract over, and so that we find out how the aggregated signature should look like. So we're just going to start by writing the first one, and we're using property-based tests. So I'm going to say for all, and we're going to have 3 integers, a int, b int, c int like this, arrow to the right like that. And we're going to say that if I have a list of a, b, and c, and I go to fold left and I use 0 as the seed like this, then if I pass in acc current, this is the function, like this, then I'm going to add them all together like this. Then whatever comes out should be, and it's going to look like this. It's going to be 0, right, plus the first one, which is a, and then whatever comes out of here like that, it's going to be plus the b, and then whatever comes out of that like this, it's going to be plus the c like this. Let me save it. And what I also want to have is that the same thing is going to work for fold right like this. Fold right, and for fold right we have this one as current and this one as ACC, and the test should still be green. So again, we want to have a function called aggregated, which is going to be defined on foldable, right? So we should be able to call aggregated on the list, and which is why we're playing with it a little bit to find out how the signature for aggregated should look like. And for now, all we can see is that we can define it for all the foldables which elements are integers, which is clearly not abstract enough. So what we're going to do is we're going to try with strings. So I'm going to copy the whole thing like this. I'm going to go over here, do that, scroll down a bit like this. I'm going to paste it over here, and I'm going to try with the strings, right? And our seed is not going to be 0. Our seed is going to be this, the empty string, and let's see what's going to happen. Now, if you scroll up, what we'll see is that that's actually strange. I wanted to show you that the order matters here, but what we actually see is that it cannot compare empty strings somehow. In fact, I've seen this thing before, and I really don't understand what it means, because it seems like it generated 3 empty strings, right? And it added them together, and the result was actually not the same as we're seeing over here. So I happen to know that the solution to this is just by switch these ones. So we have to actually go to current and add ACC, but I'm not sure how this is going to solve the issue with the empty string. So I'm really not sure what test it actually generated that failed this test, because if it tells me that it generated 3 empty strings, then for 3 empty strings, it actually should have worked. All right, so now it gets more interesting. So it seems like we can define aggregated not only for ints, but for any type that has a seed, right? So the seed over here is an empty string and the seed over here is a 0. And it has a binary operation like the plus, which happens to be, in Scala, we happen to use the same symbol for the addition of integers and the concatenation of string. So this type needs to have a binary operation. Binary means that two parameters come in, one integer over here, one integer over here, or one string over here and one string over here. And this binary operation also needs to produce exactly the same type. So we add two ints together, int comes out. We add two strings together, a string comes out. But there seems to be something more. There seems to be some sort of order involved or some sort of direction. And so we need to find a way to talk about this direction. And also it would be kind of nice if we didn't have to worry about this direction or about this order thing. So what we're going to do is for all of our fold lefts, we're going to use ACC plus current. And for all of our fold rights, we're going to use the current plus ACC. So if we switch this one, the test should still be green, okay? Like that. I'm not sure why it takes so long to compile. And now because we're using everything in the presumably correct order, we can actually start using the underscore syntax. So we can go over here and actually replace it with this, underscore plus underscore. And we can go into fold right and do the same thing over here, regular braces, underscore plus underscore. You go over here and do the same thing, parentheses, underscore, underscore plus underscore, and over here the same thing, over here like this, parentheses, underscore plus underscore like this. Now we can actually do this and we can actually do that. So it doesn't matter if we use fold left or if we use fold right, our tests are still green. What we'll also see is that in the beginning I was a bit too fast with copy pasting because fold right actually does not calculate things like this. What it does instead is it goes with a 0 and then it adds whatever comes out of this. And over here it's going to be A plus whatever comes out of this, and this is going to be B plus C, right? And we're going to do the same thing at the bottom over here, like that, just was an empty string like this. Okay, and the same thing comes out. So it turns out that the order over here also doesn't matter. So what we can do instead now is we can just go and we can say over here just 0 plus A plus B plus C, and we can just copy that and we can insert it over here like that, over here like that, and over here like that. Just use the empty string over here like this. Okay, so it doesn't matter if we use fold left or fold right, the result is still going to be the same. So to recap, we need a type with a seed with a binary operation that produces exactly the same type. So let's keep trying. So what happens if we go over here, copy this one, paste it over here, and now instead of plus, what if we use minus? Let's go over here and just put a minus over here, and let's see if that works. And it looks like it doesn't. And it turns out that it only works for fold right. I'm sorry, for fold left. So if I comment out the fold right, we're going to see that it's actually green, but for fold right, it actually doesn't work. There we go, like this. Okay. Okay, so now my head hurts. So it seems like we not only need a type with a seed, with a binary operation that produces the same type, we also need something else, something magical that we don't see, because obviously it worked for plus or for concatenation of strings, but it didn't work for subtraction. Maybe we should comment out both of these. And also notice that not every type even has a seed like this and an operation like this. So if you go over here, if we use, for example, characters, right? What is going to be a seed? Something like an empty character? Well, there's no such thing as an empty character. And also, there's no operation that can somehow combine two characters together and produce another character. You can combine, obviously, two characters and produce a string, but you can't combine two characters in such a way that another character will be produced. And by the way, sort of funny exception from this is ligages, right? So this is what fonts are doing. So this is actually two characters, one over here and one over here, but it renders them as one. But forget that I just said that. It's probably just going to confuse you. Let me comment this one out as well. And what we're going to do now is I'm going to show you a few more examples of things that are sort of aggregatable. So for instance, a string is basically a list of characters, and so lists should be aggregatable, right? So if you take this and I'm going to paste it over here like this, let me save the file so that I just compose it real quick. So instead of strings, if we use list of characters, right, like this, then the seed is going to be an empty list, right, like this. This is going to be a list dot empty of character, and the operation is not going to be plus. The operation is going to be concatenation of lists, right? So it's gonna be called like that. Okay, we implemented lists in the previous video, so you should be familiar with this one, right? So it doesn't really matter what is inside of that list, right? So it could be characters, it could be integers, right? What matters is that we're concatenating the list. We could even have lists of other things inside of it, right? We can have a list of int inside. It doesn't really matter. Okay. Let me actually revert it back to ints like this. Okay. Let me save the file. Now, before we go and implement the aggregated function, I want to show you an example which is slightly closer to praxis and slightly more further away from math. Okay. So what I'm going to do is I'm going to copy this one, for example. Right, and I'm going to show you something like this. So let's say that instead of list of integers, we had some sort of report, right? And we would be able to get out the the sort of seed somehow from the companion object, and there would be some sort of way to actually concatenate reports. And we could even call the operation plus like this if we wanted to. Okay, so I'm going to comment this out because obviously we don't have reports, and let me go over here like this. I'm going to comment it out. So what we're going to do is I'm just going to go down over here, which is still inside of the same class. Or maybe we don't even need to. We can actually go over here. And what I'm going to do is I'm going to define a tiny case class for reports. I'm going to do CC, and I'm going to call it report. Right, and I'm going to call it capital R, like this. So let's say that this was some sort of YouTube analytics or something like this. Okay, so let's say that we have subscribers like this, and we have views like this, and we have comments like this. Now I'm going to use some other types. So for example, we have comments content, which is a string, and we also have links to videos, which is going to be a list of string. And as we have already seen, like we can aggregate all of these. Okay, so we should be able to aggregate the reports. So what I'm going to do is I'm going to go over here, I'm going to say plus, and I'm going to say that report. So we should be able to do this report plus that report, so to say. Okay, and I'm going to put the function, the actual functionality into the companion object, right? So I'm going to do report.aggregate, and I'm going to say this and that, right? And so now we're going to have a companion object somewhere over here. In fact, I'm going to put it at the top, so I'm going to put it over here. Usually I put them at the bottom. Okay, so I'm going to do object report. Okay, and over here I'm going to have this aggregated function, right? Def aggregate. Okay, it's going to be that report. In fact, it's going to be R1 report and R2 report, right? Because this is going to be the binary operation, right? So now you see this in the in this notation. It's a bit more clear that it's actually a binary operation. So we need this and that, R1 and R2, and we're going to produce another report, okay, like this. And how we're going to do this? Well, we're just going to start by creating another report like this. And how we're going to do it? Well, we're going to say that subscribers is R1.subscribers plus R2.subscribers, comma, do that, duplicate the lines, put views over here, put comments over here, right? So the next time we duplicate the line, we're actually working with strings, right? So if we do over here, the operation is still a plus. And the last one, when we do this, we don't need the comma in the end. We have the links to videos, right? And as we have seen, the concatenation works like this. Okay, let's see if it compiles, if I've forgotten something. No, it looks like I didn't. It's all good. Okay, so the last thing is what we need is we need the seed, right? So the seed is basically an empty report. So if we have a seed, which is a report, right? So what we can do is we can just say report, okay? And I can actually now go and copy the stuff from here, for example, like this, and paste it over here. And these are basically the seeds. So this is an integer, this is a string, and this is a list.empty. We don't need to specify the type, but it's string, so let's go and have strings over here, right? So now we just need commas over here, and we need a comma over here. Okay, so the last thing that we need to do is we're using for all, so we need actually to tell Scala check how to generate the values. We already know how to do this, so we're going to do this like this. So we're going to go over here, I'm going to say import org Scala check underscore like this. I'm going to say implicit def arbitrary, which is an arbitrary of report, which is just an arbitrary of gen, and gen is going to be down over here. So we're going to have def gen, which is just gen of report. If this goes too fast for you, I already have like 3 or 4 videos about property-based testing, so you might want to check it out. So we're going to get the generator for integers, which is just going to come from arbitrary ints like this, and we're going to do the same thing for strings, right? And also for lists. Okay, so this one is going to be for strings, and this one is going to be for list of strings, list of string like this. So now that we have these generators, we can just use a simple for comprehension like this. We're going to go for, and we're going to get these subscribers from the generator for integers, and we're just going to do this. So we're also going to get the views and also the comments, and duplicate it 2 more times. So we have comments to content and links to videos, and this one is going to come from the string generator, and this one is going to come from the list generator. And now all we need to do is we need to yield a report. So we can just go and yield a report with, and now we can go again like this, position my cursor over here, copy that, paste it over here, have another cursor like this, have a comma. There we go. So now we can generate a report. So it looks like I haven't done any typos. So what we can do is we can go over here, and now we can generate the reports. We can call fold left. We have a seed. We have a binary operation, which seems to fulfill everything that we need, right? So we have this notion of nesting, right? So because we can aggregate integers and strings and list of strings, then we can also aggregate the reports. All right, so let's start extracting a common interface here. I'm going to call it aggregatable. So we're going to go to foldable, and in fact, I'm going to position it on the right like this, and I'm going to go and in the same file, I'm just going to go over here. I'm going to say trait aggregatable like this. Okay, so it seems like if we look at our report, so except for the arbitrary and gem, so it seems like all we need to do is we need to have a seed, right? So we're going to have a seed for some type A, which is going to come over here, right? And also we need this binary operation, right? So it's an operation. I'm going to use the functional syntax over here. I'm going to pretend like this operation just returns a function which takes 2 A's and produces another A, right? Another way to write this down would be, okay, so there's going to be A1 that comes in, A2 that comes in, and it returns an A, the same thing as we did over here. But I prefer to use this functional syntax over here. So you see that you know, this is like a thing. It's a binary operation. 2 things come in, and the same thing comes out. Okay, so I'm going to do this. I'm going to do that. And so now what we're going to do is we're going to go to report. In fact, we're going to go to the companion object of the report, and we're going to say that it extends I'm just going to copy it. I'm sure that I'm going to type it wrong. It is an aggregatable of report, right? So now we can go over here and we can say that this is actually a final override. And we can go over here, and because I use the different syntax for it, what we need to do is we need to go over here and say that it's just going to be a final override for a def called operation. In fact, I'm just going to copy it over here, right? I'm going to copy that, I'm going to paste it over here, and I'm going to say that this entire operation is just going to be called aggregate, right? And now instead of the A's, I just need to use the report, and it should compile. Right, so this companion object for the reports, it is actually aggregatable. Maybe we don't need that much space here, actually, like that. Okay, we see that the tests agree, and that should be fine. Okay, so we have the seed, we have the binary operation. The whole thing is now aggregatable. Now, assuming that we have the function called aggregated on foldable, which we're going to add in a few seconds, assuming that we have it, we should be able to go over here and do this. We should be able to say list A, B, C, and then just say dot aggregated, right? And then pass it the aggregatable instance, which is the report, okay, like this. And the result should be exactly the same as over here. So we can just copy this and paste it over here, like that. Okay, let's call it aggregated. Now obviously it's going to say that we don't have the function called aggregated, so what we're going to do is we're going to go and we're going to add it. So I'm just going to add it right under fold right. So I'm going to go and say that this is a function that is an inline def, because all it's going to do is just going to delegate to fold left or fold right, but we're going to delegate to fold left. We're going to call it aggregated, and we're going to say that it needs an instance of aggregatable, like this, aggregatable of element, right? From this element that comes in over here. And what should come out is also an element like this. And what we're going to do is we're just going to call fold left, and we're going to say that the seed is going to come from the aggregatable.seed, and the operation is going to come from aggregatable.operation, right? So you see all the signatures over here, so it's going to fit over here. Now the thing is that we have to do this covariance stance because we have a plus over here. So what we need to do is the same thing as we have been doing all along. Just going to do this super element, and now instead of elements over here, we're just going to use super. super like this. And now everything should be good, everything should be green. And in case it's not obvious, we're going to use it as a type class. So we're going to mark it as implicit over here, and this should allow us to go over here and copy that line and not to specify the instance of aggregatable. And obviously it's only going to work if we're going to go to the companion object, for example, and somewhere in here, if we're going to say, for example, implicit lazy val, it doesn't matter how we call it, but we're going to say aggregatable, which is an aggregatable of report, and we're going to do something like this. But this is not common to do actually, so we're actually not going to do this. So we're going to refactor our companion object instead. So instead of just using this over here, we're going to create a new aggregatable over here, new aggregatable of report, and now we're just not going to do this. It's kind of ugly anyway. Over here, let's just go there. In fact, we don't need to make it lazy. We can just do lazy val like this. We can call it like that. Somehow prefer to call my instances like this. Okay, so now we just need to move the seed over there. All right, so we're just gonna move it. Oh, okay, like this. There we go, like this. Okay, the seed is now over here, and we also need to move the operation. So I'm gonna cut it out. I'm gonna paste it over here. Okay, now a few things are not going to compile. For example, we go into report.seed over here. So we're going to go to report.aggregatable. Aggregatable. Come on, aggregate. Man. All right, aggregatable.seed. We don't get the auto completion because I actually called it was a capital A, like this, capital A. In fact, this time I'm going to call it with a small a. I don't know. Maybe I'll change my mind later. Okay, so we have the aggregatable seed, and we also need to use it over here like that, right? All of these 4 places. Let's create even more space. Let's see. Also, I think at the bottom, yeah, we'll go to report.aggregate this and that. No, that should still work, right? Yeah, that should still work. Like this, but we could actually also go and oh yeah, so report itself is not the aggregatable thing anymore. It's like that aggregate. Come on, what did that aggregatable like this? There we go. Okay, so what does it say? Value aggregatable is not a member of object user report. What do you mean? It's right there, aggregatable. Oh, it's actually line 147. So let's go over here and put it over here. All right, let's go and see. All right, looks like it's fine. So again, so now we have this companion object report, and inside of it, we have this instance, which actually, I don't want to have this aggregate anymore. So I'm just going to go and I'm going to say that it's going to be over here, R1, R2, arrow to the right, and I'm just going to copy this entire thing in there like this. And therefore, we don't need the aggregate. And somewhere at the bottom, we're actually using it, right? So I'm going to go to, I'm going to call this operation, and we're going to call it on aggregatable. Okay, please help me. There we go, like this. All right, there we go. Refactoring, running, green. Cool. Now let's go back to foldable. I actually want to show you that we can actually use the context bound notation over here. And for this, it's common to also define a summoner. So we're going to define a summoner for aggregatable. And again, if this goes too fast, I already have videos about implicits and about type classes, and you might want to rewatch them. Okay, so it's just going to be aggregatable of a, and it equals implicitly aggregatable of a, like this. Okay, so now over here, instead of using I'm just going to create more space like that. I'm going to duplicate that line so that you see that it's actually the same thing. So I'm going to do aggregatable, right? So basically saying this is going to work for any super that has an instance of aggregatable, and now we don't need this implicit parameter. But because we don't have this implicit parameter, we don't have access to this aggregatable instance, right? In fact, let me swap the lines over here and comment this one out. Okay, so this is exactly what the summoner is for. So now where we say aggregatable, I can just use aggregatable like this and just specify the type by just giving it the super like this, and it still should compile. So this is exactly the same thing. So you can actually mix the lower bound and the context bound over here, right? Let's go like that. There we go. All right, so it seems like we have found our pattern, and mathematicians have found this pattern as well, and they studied in multiple related branches of mathematics. The most prominent one is called group theory and subsets of it, like for example, there's also the semi-group theory. This pattern is also studied in the category theory, one of the most abstract branches of mathematics, but we're barely going to touch upon it today. Let me scroll up a little bit. So how do the mathematicians call it? Do they call it aggregatable? Well, no, they look at it and they give it the name in terms of its operation. So if we look, all of the operations on aggregatable, they essentially produce 1a, right? So what the mathematicians do is they call it one-like or one-ish or like one, and they use Greek. So one in Greek is called mono, and the suffix that means like or ish is called id. So it's called monoid, and it's pronounced monoid. So what we're going to do is we're going to go and rename it. Where we say aggregatable, we're just going to call it monoid, like this, and probably our test not going to compile. There we go, aggregatable. Let me see that I use this, and there we go. So we're going to have monoid over here, and we can actually use monoid over here, everywhere, like this, monoid, like that. And it's green. Also, even though we're not going to rename it now, but this seed has also different other different names. We're going to do this actually a bit later. So sometimes it's called identity, sometimes it's called zero, sometimes it's called neutral element, actually in German. Yeah. All right, cool. So now we have this aggregated function, which is defined on foldable, but we cannot always call it. It doesn't work for any element. It only works for the elements which have an instance of this monoid. And as we have already seen, there's also something a bit, there's also a bit more to it, right? So we can actually create an instance of monoid that will compile, but it's not going to be a monoid, right? So for example, with the subtraction operation, we have seen that it didn't work for some magical reason, for some magical ordering or direction. Now, this weird ordering or direction thing has a name in mathematics, and it's called associativity, or it's called the associativity law. And what we're going to do now is we're going to create a tiny mathematics library which will define these monoids, and it will work in such a way that whenever we define an instance of a monoid, if we use it for the first time, we're going to make sure that this law holds by using property-based tests. Now, this is not how first of all, it's still going to compile, right? Even if it's wrong, it's still going to compile, but at least at runtime it's going to fail earlier. Before we start doing this, I want to mention a few things. First of all, usually when we create libraries, I separate them into separate jars so that I make sure that the direction of the dependencies is being maintained by SBT. But I want this project to be self-contained. So what we're going to do is we're just going to create a sibling package to the Homegrown collections, right? So we're going to have Homegrown collections, and we're also going to have Homegrown math library. In fact, I'm going to go and I'm going to create it right now. We're going to go new folder. I'm going to say math library, okay, like this. So it's over here, right? So another thing that I'm going to say is that usually if this was a production level library, I would not define it like this, because we're going to be forced really soon to use Scala check in the production scope and not only in the test scope. So if I go to the build file, for example, and I look for Scala check, Scala check like this, then we see that we're only using it in the test scope, but we'll be actually forced to use it in the production scope as well. So in fact, I'm just going to do it right now. I'm just going to go here, I'm going to go here, I'm going to reload it. It should go really fast. Come on, there we go. I'm just going to test it again. Everything should still be green because we haven't really changed much, right? So now we have access to Scala check in the production scope, and this is one of the reasons why I actually wouldn't do it in such a way if this was a production level library. But right now this is an education level library, and I believe for education this is actually a kind of nice approach. In fact, let's go there right now to the math library, and we're going to start by creating a package object. So I'm going to create it like this. I'm going to call it package.scala. So now let's see if it created it in the correct folder. Yes, it did. It's right there. All right. So let me create a bit more space. We actually don't need the build file anymore. Okay. So I'm going to say package homegrown, but now I'm going to say that it's going to import org.scala check prop, like this, okay? And we're going to say package object math library, okay, like this. Okay, so again, we need a set of values, which is basically a type. Let's call it A, and we need a closed binary operation on it. Binary means that it takes two parameters in, so I'm going to define a type ls. I'm going to say closed binary operation for some a, right? And binary means that it takes two a's, binary, two, right? And close means that it has to produce another a, like this. Now the type system is going to ensure that an a also comes out. It basically is going to ensure that the operation is closed as far as it actually can. So for example, if we have integers and we have the division, right? So if we divide 3 by 5, the type system is going to make sure that the integer is going to come out, right? So we're going to lose some precision, but an integer comes out. Also, if we divide 1 by 0, an exception is going to be thrown, right? In Scala, and a thrown exception has a type nothing, and the nothing is a bottom type, which means it's a subtype of every type, also of this type a, which is why it's going to compile. So we need to remember these things. By the way, if you have a set like this, so a type in programming, and type a is essentially a set of values of type a. So if you have a set like this and you have a few operations defined on it, then this set is called an algebra, and this structure where you have the set together with the operation is called the algebraic structure, which is very much related also to algebraic data types, which in Scala are expressed with a sealed trait or a sealed abstract class, and a few ways to construct this this class. So we're going to talk about mathematical laws over here. So what we're going to do is we're going to go over here, and I'm going to say that we're going to have a alias mass library like this, and what I'm going to say is that a type law is going to be arg Scala check dot prop, right? So we're gonna write properties, but they're gonna make sure that some mathematical laws are gonna hold. So we're just gonna have a type alias for prop from Scala check. And also, we don't want our users, which is gonna be us in our test, we don't want to force ourselves to import many things from Scala check. So we're sort of trying to hide Scala check a little bit as much as we can. So what we're gonna do is we're also gonna create type aliases for arbitrary and gen. I'm gonna go over here. I'm gonna say type arbitrary a is actually org.scala check.arbitrary a, right? And I'm going to do the same thing for gen, right? So I'm going to go over here. I'm going to say that this is a gen as well, and also for the objects as well. So I'm going to do inline def arbitrary, which is an org.scala check.arbitrary.type equals org. I'm going to do this over here, org.scala check.arbitrary. And I'm going to do the same thing for gens. Okay, so I'm going to go over here. This is going to be gen. I'm going to go over here. This is also going to be gen. In fact, maybe I should also do that like this, and over here like that, and over here like that. Enter, and over here like that as well. I'm sort of starting to get used to this syntax. Oh, Scala reform went and ruined everything. We want to go and formally define this this property of closure, right? So we're going to have closure, and we're going to say, okay, if I have an A which has an instance of arbitrary, well then I can have an operation which is a closed binary operation on A, okay, and I'm going to produce a law like this. We need a bit more space, like that. Okay, so now what I can do is I can go, in fact, you know what, we're going to do it like this. We're going to do it like that so that I don't need that much space. So we're going to say over here, we're going to say that for all A1, which is an A, and A2, which is an A, okay, if I stick them into an operation, A1, A2, then what should come back is A3, which has exactly the same type. Now, as I already said, I'm sorry, I wanted to return true over here. The type system is going to help us out over here. Okay, so it's actually impossible to produce anything else apart from A in this case, unless we throw an exception, but technically it's also an A. The next thing that we're going to do is we're going to go and we're going to create a file called group theory, right? So we're going to create group theory.scala. It's going to be exactly in the same folder over here, right? So if I press save and I reveal it in the sidebar, it's going to be exactly over there. So we're going to have a package. Homegrown package. Let's actually not do this. Let's do homegrown dot math library like this. Okay, so it's a convention sort of in Scala that if you have a trait that has like only one operation, then you can call it has that thing. So we would call it has operation like this. Okay, so it just has an operation which is a closed binary operation like this of A. It's called has operation. Now, for some reason in group theory, this thing is called a magma. I have no idea why. I'm going to leave a comment over here. It just says has closed binary operation of A. Okay, just so that you remember what a magma is. I have no idea why it's called like this. Now, later we're going to use this magma as a type class. So what I'm going to do is I'm going to go create a trait that will help us with the summoners. So I'm going to say, okay, this is going to be a summoner of B like this, define, apply. It's going to look very cryptic. A, B, BA, right? And all it does is it goes to implicitly and gets out the BA. So now if I go over here, let's see if it compiles. Yeah, it does. So now I can go over here and can say that this is an object magma, and it just extends a summoner for magma like this, right? So this magma is going to become a B. Magma is a class which has one hole over here, right? So when we call basically apply on it, we can use magma like this, right? So we can basically retrieve a magma by just saying, okay, give me a magma for ints, for example, right? And it's going to give it to us. So as we just learned, a magma is an algebraic structure, right? So we're going to go and say algebraic structure. So today we're just learning a bunch of new words. Okay, so this is an algebraic structure for A. So I'm going to create a new file, and I'm going to call it algebraic structure. God help me to spell it correctly, like this. So I'm going to go back to group theory for a bit. I'm going to copy the package, and I'm going to copy this, right? So it's just going to be a trait like this, trait. There we go, algebraic structure. Let's see, that should be enough to get it to compile. So the last thing that is left to do is to combine the laws with algebraic structures. And the way we do this is just by going to the companion object of the algebraic structure that we're going to create in just a few seconds, and call ensure laws hold by giving it laws. And laws is just going to be a protected def. Laws like this was a set of law. Okay, so what we're going to do is we're going to go and create algebraic structure like this, which is the companion object for the trait. So we're going to go and say private def ensure laws hold. It can be private because the only place where we're going to call it is from this trait. So ensure laws hold and gets the laws, which is a set of law, right? And it just does unit. So all it does is it combines all the laws into one by just saying laws dot reduce like this, right? So this is not an operation for booleans, this is an operation for properties, but it works essentially the same way. So you can combine a bunch of properties into one. So reduce is sort of like fold, but the types have to be it's actually sits somewhere between aggregated and fold, and it will throw an exception if there are no laws, which is sort of what we want in this case. Okay, so now all we need to do is we need to go to this law that we have accumulated, aggregated, reduced, and we just call check on them like this, and this should be enough. Now we need to go to group theory and go over here, and now we can say that we're gonna override protected def laws, which is a set of law, right, like this. And what we need to do is we need to say that this is going to be a set with closure for this operation. Okay, so again, we have closure defined over here, closure, and we need to go to group theory. So we have closure, we pass it the operation. Okay, so this is what the closure wants. It wants an operation, and we put it in a set, and now we can override this protective def laws. Now it doesn't compile because it says couldn't find implicit value for evidence parameter of type homegrown, blah 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 blah. So if you want to call that over here, then we also need to have this instance somewhere, right? So we need to go and say protected implicit def arbitrary. It doesn't really matter how we call it. It's going to be arbitrary, and we don't need any imports because we have this type alias, right? So in this package we have this type alias for arbitrary, and therefore over here in group theory we can just go and use it straight away. Now unfortunately we can't play with this closure property, but we actually can play with the next one, which is associativity, right? Because closure, the type system is gonna help us out, so there's no way that we can manage to fail this test. But we can play with the next property, which is associativity, which happens to be the actually kind of the most important one for programmers. Associativity like this. Okay, it's going to look exactly the same way. A arbitrary like this, right? It also wants an operation. Let me duplicate it, bring it down like that. So it's going to produce a law, and it's going to call it for all, and we're going to have A1, which is an A, A2, which is an A, and it actually needs a third one, which is an A, arrow to the right. Okay, like this. Let me scroll down a little bit. Okay, so what is associativity? Associativity is a property where we're gonna go and say format off, format on. It's gonna help us out. This is the thing that we have seen in the beginning was a fold left and fold right. Was a parentheses. So if we call an operation on A1 and A2, and then we take this as a result and we stick it again into the operation, right? We stick it again into the operation with A3, then it should be the same thing as doing it was a different grouping, so to say. It's not really order, it's a different grouping, right? So if you're gonna have operation of A2 and A3 like this, okay? So let's see. Yeah, it compiles. Okay, we're obviously not running this yet, but we will soon. And because also I want you to see this the syntax was the parentheses, the ones that we have seen was a fold left and fold right. We're actually also going to go over here and we're going to define a tiny syntax. So we're going to have implicit final class. We're going to call it infix notation. We did a similar thing in the series about monoids. So we're going to have a private val. I'm going to call it A1, which is an A. We can actually extend any val over here like this, and we can go and say inline def. We're going to call it combine. I don't have a better name for it. So the idea is that A1 comes from here and the A2 comes from here, right? This is A2, and it's still a binary operation, so A should come out. And the thing is that for this to work, we actually need a magma. So what I want to see over here is I want to say that if there is a magma defined for an A, then I can use it over here. Magma dot operation A1, A2. So we need to specifically request a magma over here. So we need to go implicit magma of A, right? So if there is a magma defined for an A, then we can use A1 dot combine A2 instead of doing magma dot operation A1, A2. Like this, okay? So now what I can do is I can go over here and I can say that I don't need only this to be an arbitrary, I also need to have it a magma. And so if it has a magma, then I can actually go and use combine. In fact, before we do that, let's actually use a magma over here like this, and now some code is not going to compile. Okay, so we need to go to group theory. In fact, I'm going to put it over here. And we need to say that, it's a similar thing that we did was the report in the very beginning. So we're going to go over here. We're going to say final protected implicit def. I'm going to call it self. It's going to be magma of A, and it's going to be this, right? So in the beginning, I said that I don't want to do this, but in this case, this is exactly what we need. So now we can go back to the package, and we can do the same thing for the associativity. But before we do that, I can actually use it over here, right? So instead of this, now we can just say A1 combine A2, right? Or we can do A1 dot combine A2 like that. Okay, so obviously I need to call them differently. A4, A5 like this. In fact, we actually don't need the left side, so I'm just going to do this and that, right? So this is the closure property, right? Actually, it's kind of, no, this is better. A3, A3, A like this. Okay, so this is better. So this is the closure property. You take two A's, another A comes out. Okay. Now, for the associativity, is actually going to make more sense, because if you use infix notation, then we can see that if we have chaining, right? So it means that we have A1 combine A2, and we combine it again with A3, which is effectively just chaining, right? So it's A1 combine A2, and I'm going to go over here, and I'm just going to do, come on, we're almost there, like this. Right, and we do again, it's a chain, right? Combine A3, and now if we also have a nesting, right? So if I have nesting like this, in fact, I'm going to do it like that, or maybe like that. I sort of wanted to align, okay? Then if we have A1 combine A2 combine A3, right? I want to have it like this, or in fact maybe like that, even like that. Okay, right, then this is basically, oh my god, why did it jump over there? Right, so this is A1 dot combine. Now I'm going to open the brace and I'm going to close it somewhere over here, in fact, like this. Let me press tab over here, tab. Okay, and now over here, oh come on, over here I'm going to have A2 dot combine A3. Okay, let me comment this out as well, like this. I just want to show you why it's nesting like this. Okay, so this one is just a chain of calls, and this one is a nesting of calls. So it doesn't matter if you chain or if you nest. What happened over here? Like that, and like that. There we go. Yeah, that's how I wanted. Okay, then it basically says that chaining should be the same as nesting. Okay, what did I do? I forgot to request a magma. There we go, magma. There you go. Okay, so if there's a magma for A's, then you can use this syntax. So usually it's introduced as, you know, it doesn't matter how you put the parentheses around, which is what we have seen in the beginning with fold left and fold right. So in fact, I'm gonna remove this because we don't need that anymore. So now we can go to group theory and start actually using it. So a magma that is associative is called a semigroup in group theory. Semigroup of A, it extends a magma of A, right? And it has the same stuff over here, like that. So it has laws, and we're just gonna put the laws together, right? So we say that all the previous laws, they still need to hold, plus we need the associativity for the operation, right? So now we need both, and we also need the summoner probably at some point later. Right, so we're going to do semigroup, right? That's exactly why I created this trait. Okay, so the semigroup is actually the first one that we can play around with. So I'm going to go to the to package over here. In fact, I'm going to throw the should I do that? Yeah, I'm going to put the group theory over here to the right. So it's now over here so that we can see how these things look like, the semigroup, for example. Okay, so I'm going to go to the package object over here. And somewhere at the bottom, I still want to be inside of the package object. So somewhere over here, I'm going to go and define one instance for a semigroup. So I'm going to say implicit val, and this time I'm going to use capital addition, which is going to be a semigroup for integers. It's going to be new semigroup for integers, like this. And inside of it, I'm going to say, final override, protected, implicit, lazy val, which is pretty much all the keywords that we need. And by the way, if we're overriding something that is implicit, we actually don't need to use the implicit keyword like this. In fact, in this case, it's actually going to cause us problems. Okay, so it's going to be called arbitrary, which is an arbitrary of ints, right? It's going to be implicitly arbitrary of int. And by the way, we need to do this thing because there's no summoner for an arbitrary defined in Scala check, so we need to use implicitly directly. Okay, and now all we need to do, we need to final override lazy val operation, and it's a closed binary operation for ints, and the operation is going to look like this. It's just going to be add, right? Take these two things, take these two A's and add them together. Let me create a bit more space like this. Lazy val arbitrary overrides nothing. It means that there's a typo somewhere. Okay, this one looks correct. Arbitrary. How did I call this one? I called it arbitrary, obviously. Come on. Happens so often. All right, there we go. And I believe, in fact, if we use the implicit keyword, let's see. Okay, in this case, it actually works, but I'm not going to use it. I'm gonna do this. Okay. So it just needs to be implicit over there. Okay, so again, a semigroup is just an operation, but it also needs to abide all the laws. And this is what we still need to check, right? So we need to go to something that's runnable, right? So we need to create a main method, or we need to create a test in which we access this val, right? So as soon as we access this val, it's actually just going to be, you know, sort of instantiated, and the tests are going to run. So I think maybe we should go and do this. So let's go to list suite, and we're going to create a new file over here, and we're going to call it group theory suite.scala, like this. Okay, so let's go to list and go up, and I'm just going to copy this. I'm going to say group theory suite like this, and I'm going to say group theory suite like this. I'm just going to have a test. I'm going to call it group theory like that. There we go. Save that. We don't need the list anymore, and now we can actually start running only this one. So we can say test only user dot group theory suite like this. So all we need to do is we need to actually touch it, right? So we can say, for example, int addition. I'm spelling with a small I, right? We can say that this is a semigroup of ints. And by the way, this should be math library, by the way, math library. Okay, this is what we're testing, right? This is a semigroup, and I'm just going to say int addition. Okay, like this. So now we actually see that some tests ran because we see this print line from Scala check, which is not ideal. I don't want to see anything if the tests are green. Also, let's go and define a string concatenation, right? So we're going to go over here, and I'm going to call it string concatenation, like this, right? So it's not for ints, it's for strings, and it's still called plus, like this. Okay, so let's also go to the group theory suite and do hold up string concatenation like this. String concatenation like this, and this is a string, and this is a string like this. Oh my god, did I call it wrong? Concatenation. It's like this. I believe it's spelled like this, isn't it? So again, now we see actually two print lines, which is not ideal. I don't want to see them at all. We're going to fix this in just a few seconds. For now, I want to show you that you know, it should fail for the subtraction, right? So if I go to package, and I'm going to take this, and I'm going to do right int subtraction, and all I need to do is I need to have a minus over here. I need to go to the test. I'm going to do that, and I'm going to do subtraction like this, and subtraction over here, subtraction over here. All right, so if we scroll out, we see a different print line. So we see that it actually failed. Now, what we're going to do in just a few seconds, we're going to build it in such a way, you know, we're going to dig a little bit deeper into Scala check, and we're going to make sure that it actually throws an exception if this stuff happens, right? But as we already see, this is actually not a semigroup, right? So again, so if the operation doesn't fulfill these laws, it means that together with on the set, it does not form this algebraic structure. So in this case, it does not form a semigroup. I'm going to leave it here because I want to see the thrown exception. So what we need to do is we need to go to the algebraic structure, and we need to change this code a little bit. First of all, let me line it a little bit like that. Okay, so this is essentially just one line. Okay, so instead of this, let me scroll down. Right. Okay, let me go save it again. Okay, so instead of this, what we need to do is we need to say test.check. We need to pass in some parameters, and then we need to pass in the law, right, which is this. Okay, so instead of this, we're going to have this line over here, and for this we need a few imports. So we need an import to Scala check like this, and we need the org Scala check test like this. Okay, so the test comes from Scala check, which is this one, and some other things that we're going to use in just a few seconds are going to come from test._. Okay, so now all we need to do is we need to find define these parameters. So it's going to be just a private val over here, private val parameters, which is just parameters. Okay, like this. So we're going to do parameters dot default like this, and all we need to do is we need to change the callback. So we're going to say with test callback over here, and we need just to pass in a new instance of test callback like this. Okay, so I'm going to say final override def, and it's called on test result, has a name which is a string, has a result which is a result like this, and just produces a unit, right? So over here we're just going to say, so if result passed, right? So if it's not passed, then in this case just throw an exception, sys.error, and it also has a utility to print the result, pretty result. Okay, I believe that this is actually all that we need. So as you can see now an actual exception is thrown, exception and initialize error, right? So usually it's not ideal to throw exceptions in the constructor, but in this case this is exactly what I want to have, right? So if my users, or in this case, you know, if me, if I create something that compiles but it is not a semigroup or it's not a monoid, then I want it to explode as early as possible, and this is the earliest place possible, right? So, and this pretty printing gives us exactly this. Okay, so now if I go and I remove in subtraction, I'm just gonna throw it out like that. Okay, like this, and go to the group theory suite and remove subtraction from here. Then if I scroll down, everything should be green, and now if I go to algebraic structure again, if you see this code, right? So we only throw in an exception if the result hasn't passed, and otherwise we're not printing out anything, right? So if the tests are green, we're not seeing anything, right? This is exactly what we wanted. This is just a bit of code like this. This is all we needed. We can actually throw this one out, right? Just a few lines. We're just replacing the test callback for Scala check, which I have to say has been quite easy to use programmatically. I'm super happy about this once I figured this out. All right, so what we're going to do now is we're going to go and define semigroups for our lists and our sets. So because Scala check is available now in the production scope, we can actually go into the package object, which is in source test Scala user package. Let me go like this, reveal in sidebar. So it's somewhere in the test folder, and what we can do is we have an arbitrary and we have a gen for sets and for lists. So what we're going to do is we can cut them out like this, right? Like that. Save that. Go to list.scala. Go down into the companion object and define them somewhere at the bottom like this. And now we can also call them just arbitrary. This one is just arbitrary. This one is just gen. And yeah, this one not gen, not empty, like this. And we need to fix the imports a little bit. So we're going to say package homegrown, package collections, and we're going to say import math library. Right, very important. The homegrown collections, it can use math library, but not the other way around. I don't want to have cycles. And in fact, maybe we should also run all the tests and not only whatever we're running right now, group theory suite. So I can go like this, run all the tests, make sure that they're all still running, and then we can do the same thing for the sets. So just gonna cut this out, these arbitraries like this. Go to set.scala, go to the bottom, paste them over here, say that this is just an arbitrary, this is not gen set, this is just gen, this is not gen not empty set, this is just gen not empty. Go to the top and actually go to the list and do that over there as well. Cool. Okay, so now we can go and actually define a semigroup for lists and a semigroup for ints. Maybe we should start by copying them. Yeah, so this is the string concatenation. So let's go, for example, to lists at the very bottom. Just insert it over here. And now we can say that this is a list concatenation. Just use list everywhere. And in fact, we can just call it concatenation because we're inside of list. Okay, and that's how it works, like this. There we go. What's up? Class list takes type parameters. Yeah, obviously this needs to be a def, and this is going to be an element. I'm just going to use a, which has an arbitrary. Okay, so this is not going to be a semigroup for a list. It's going to be a list of a. This should be enough, right? Yeah, it looks like it's compiling. So I'm going to do the same thing, and I'm going to go to sets, and I'm going to paste that over there. And I'm going to say that this is a union, right? Union, because the operation is called union on the sets, right? And everywhere where it says list, just going to say set like this. Okay, there we go. Awesome. Something's compiling. It should be enough. Now, as I already mentioned, I really don't want to have a cyclic dependency over here. So it's okay for the collections library to use the math library, but not the other way around. So we cannot go to the group theory suite and put some tasks for an instance that is over here. In fact, right now it would compile because we just created, everything is in the same project, right? It's just a different package. But I still don't want to have this, right? So I'm going to go to list suite. I'm going to go down. This is where we were actually in the beginning. So I'm going to go somewhere over here. I'm going to call it group theory again. Group theory. Right, it's fine because it's in a different suite. And what I'm going to do here, I'm going to say list of int concatenation is a semigroup of list of int, right? And it's just going to be a semigroup of list of ints like this. Let's see. Not found value. Okay, we need some imports. Okay, we need to do this, and we need the math library like that. Okay. All right, cool. So it's over here. Let's do the same thing for strings, even though it doesn't really matter what is inside, as I already mentioned. Okay, just for fun, can use strings over here like this. And also, by the way, we can retrieve the semigroup like this, and we can also go just to list, and we can say concatenation of strings like this, right? So this is just an alternative, and obviously I have a spelling mistake here. Oh my god, concatenation like this. Right, so this is always better, always better than this one. Okay, and I'm gonna do the same thing for the set suite. So I'm gonna go set suite and go to the bottom somewhere over here. Group theory. Okay, let's do set, and concatenation is called union, and this is still a set. Whoops, too much. Set, and I can go back to the suite and copy the imports. Like that, set suite, replace them over here, There we go. Everything should be green once it finishes compiling.